Hello again. Today we're going to be talking about how to find the arc length of a curve when it's graphed on the XY plane. So let's get started. Let's say I have this graph and I want to know the length of the curve from endpoint to endpoint. So I could approximate it, but how am I going to do that? Well, I'm going to go through the same process that I did with derivatives and integrals and make an approximation, make that approximation better, and then make it more exact until I come up with a formula that I can use all the time. So my first approximation would be, well, what if I find the length of the secant segment that goes from endpoint to endpoint? How would I actually find that length? Well, the horizontal change from endpoint to endpoint, I could call that delta x, and the vertical change from endpoint to endpoint, I can call that delta y. So Pythagorean theorem gives me the square root of delta x squared plus delta y squared. Now, if I manipulate that a little bit by multiplying by delta x over delta x, that becomes delta x over the square root of delta x squared, which can then be brought over with the other square root as its denominator instead, and then it becomes the denominator of each of those things in the square root. So I get delta x squared over delta x squared plus delta y squared over delta x squared, and I still have that delta x outside of the square root. And then delta x squared over delta x squared simplifies to be 1, and the delta y squared over delta x squared can be simply written as 1 fraction squared, still with the delta x outside of the square root. So I'm going to use that as a way to approximate the length of the curve by measuring the length of that green secant segment. All right, obviously that's not a good approximation just by looking at the picture. So what I could do is I could add several secant line segments together. I could space them out however I want, and that gets me a sum of that same formula over and over again, that square root of 1 plus delta y over delta x squared with the little delta x outside the square root. Now there's going to be a bunch of delta y's and delta x's, so I have to call each one of them delta y sub I and delta x sub I, and then add all of those together. And that would get me a better approximation depending on how far I separated the x's and the y's along the curve. So if I use more segments, then obviously it's going to be more accurate. But if I use an infinite number of those segments, now my sum becomes an integral and the changes in x and y become instantaneous. So it's not delta x and delta y anymore, it's dx and dy. So that sum becomes an integral from endpoint A to endpoint B of the square root of 1 plus dy over dx squared dx. Instead of those deltas, now I have d's. And I can write dy dx as f prime of x, and the rest of the formula stays the same. So here's an example. Let's say I have this curve right here, and it is the curve of the function y equals x to the 3 halves, and I want to measure that from x equals 0 to x equals 4, just like it is in the picture. Well, there's my formula for arc length. I'm going to use that formula from now on to calculate arc length. And so dy dx, if y is equal to x to the 3 halves, then dy dx is 3 halves times x to the 1 half. And I plug that in to the formula. I square it, and I get 9/4 x. Everything else stays the same. So I am going to do a U-Substitution so that dx equals 4/9 du. And now if x equals 0 and u equals 1, if x equals 0, then u is going to equal 1. And if x equals 4, then u is going to equal 10. I got that by plugging in those x values into the equation u equals 1 plus 9/4 x. And that got me to my u values, which I can use in my integral because now my integral is in terms of u. So now my integral is 4/9 times root u from u equals 1 to u equals 10. All right, or u to the 1 half instead of root u. That means I can use power rule. So it becomes 4/9 times 2/3 u to the 3 halves evaluated at 1 and 10. Or I can multiply the 4/9 times the 2/3 and get 8/27, but the rest of the question stays the same. So my answer actually becomes 8/27 times 10 root 10 minus 1 in parentheses. So that's the formula that we're going to be using to find arc length, and that's kind of where it came from. If you have any questions about that, please let me know, and I will see you tomorrow.